Welcome to this tutorial produced by CertaSIM LLC. It shows how to build a model from scratch in the IMPETUS AFEA Solver GUI editor mode. We will see the interface and actually build a model. The model that we're going to set up is shown here. It consists of a solid cylinder that's 1 meter long. It's a radius of 5 centimeter. It's constrained in one end. It's pulled in the other one. This is done by displacement. That's 10% of the initial length, and this is a prescribed motion. The cylinder is a mad elastic, which has Young's modulus and density and Poisson's ratio is shown here. The event time is 10 milliseconds. The mesh is a butterfly mesh with n equal to 4, so we have 4 by 4 elements in the center of the butterfly mesh, and we have 10 elements along the length of the cylinder. So let's go in and start doing the model. So we go into the IMPETUS AFE solver. We select a new file. We can call it cylinder or cylinder test.k, so that's our command file. And there's a folder so we can save it where we want to save it. We could use a wizard that goes in and give us, for example, possibilities to guide us through time and things like that, the standard commands. But let's just go directly and open it into an editor mode. So now we can start. So this is basically the editor mode. We can start typing the model here. We have on the right side, we have the manual over here. And we have different options that we will cover in other tutorials, like for example, starting a simulation and view the input in that interface as well. So we can start with a comment that we do that with the pound sign. So we can say testing. Now this is for one line. If we want to have more testing or more testing information, we could do multiple lines, and we just have to do brackets here, like this one here. Say, hello world. It is a great day. And then we will have to end that block of text here. What we like to do is, I think that's very convenient if you have to make changes, is to put in parameters. So as much as we can parameterize it, the better it is for quick changes. We saw the setup before. We need a radius, and there's other things that we need in order to build this model. So let's start to put these in, and then you can see how these are used. We had a length here. That was 1. We have a displacement. That was 10%. So we just do it like this. Then we had end time. We can set that to 10. We can set that to 10 milliseconds. Now we're using the SI unit system in this model. Then we had a mesh parameter for the butterfly mesh for 4 by 4 in the inner part of the butterfly. Then we had a mesh of 10 in the axial length, 10 elements. And then we're using elastic material, so let's just put in some material parameters for that. Stiffness, Young's modulus. We have a density. Then we have Poisson's ratio. And this is basically the parameters that we need for this small model. So like this is easier to read when we kind of split up the input deck in this way here. We need to have a time. The time was up here, so we can do it like this. Let's see here, that was called it's called TN. This is how we call one of the parameters, and you can see it gets highlighted there. So it found it, which is very important, because if we can't find it, then we have a problem, of course. Perhaps we misspelled or something like that. So now we want to build the mesh. So let's do that with one of the built-in runtime features. And here we have the component cylinder. We have to give, as you can see, the manual over here now tells me that, okay, I need an ID and I need a part. So let's just call it part 1. And then it needs the mesh sync parameters. So we will have to do the length, and then we have the butterfly in a butterfly here. And now we need to give a start and an end of this cylinder. So basically you need a face point. So why don't we put it in 0, 0, and then we want to do it, if we do it like along the x-axis, then we could do the length here, and of course the rest will be 0 as well. And we could see here that we also need a radius, of course. So, and that parameter we had here as well, that was r. So now this is the model. Basically, this is the mesh. Defined very simple. Now we need to give this a part. So let's do a part, call it 1, because that's what we're calling up under the component cylinder. We need an ID of a material. Let's just call that 1. Now we need to specify a material. And you see there comes all these list of the different commands. So I just picked the one that I wanted to use here. Mad elastic, we need and again the syntax is to the right. So this one, this space here is the density. And then we have Young's modulus. And then Poisson's ratio. What this is also good for is that if we have changes and calling the same Young's modulus from different materials, then if they're not using the same ID, of course we can change it up in the top here. So we need Poisson's ratio. And now we want to put in the boundary condition. Boundary conditions like constraints is done with BC motion as well as it also take care of like prescribed motion. So now we can do it different ways, but first we need an ID. Then we can do it on geometries, which makes sense because if you're doing a change in mesh, you don't really like to do a node set. That's kind of an old-fashioned legacy codes way of doing it. So let's just do it on geometry, and let's use geometry 1 here. Now we have the boundary condition. Let's just constrain it. So we do it x, y, z. So we translation and constrain it in one end. And we then have to, of course, to make that geometry. So let's use a seed coordinate because that would make it independent on the mesh. But we assume that we're not moving that cylinder in space. So let's just do a seed coordinate. And that would be for 1. So that's the ID 1. Now we had taking 0, 0, 0 as the end of that cylinder. So let's just use that. I'll constrain it in the end there, and then I will go in and we'll do another motion. We need to do the prescribed motion, but I could do, let me just do the geometry first for that when we are thinking about it. So that would be 2, and then it would be the length along the x-axis. So that will be L, and then that will be 0, 0 as well. And now I can go down and I can do the boundary prescribed motion. And see here, there's no order that have to be followed here. So I can do it in any arbitrary order that I want to do. Of course, the parameter is placed in the top of the command file, and then I have star end always at the end. But otherwise, can be placed wherever I want to do it. So you see here now I'm switching around. Before I did the boundary condition first and then the geometry. Now I'm just doing the geometry and afterwards the boundary condition. So we call that 2 here. And we want to do a geometry again, and we use geometry 2 that we already gave. And then I don't want to do constraints here, but what I really want to do is a prescribed motion. So I go to the next line. It's called the P method because that stands for prescribed method. So I would select, let's just select displacement. What direction would be the global x direction. Now I can do a function, I can do a curve. The function is actually a very powerful option in the IMPETUS AFE solver. For example, I can, in my material model, I can do the hardening law using a function, so that gives me a large flexibility. But in this case, I'll just do a curve here for the simple linear curve actually. So let's just get a curve and we'll call it 1. Now I want to have the displacement starting in 0, 0. And what I'm doing now is not necessary, but what I like to do is, and it's an old habit, I guess, but I like to take and extend a little bit my last point when I have a linear case like this. And anyway, I can do that. Um, so I will have to do it both for the X and the Y. So we can do here, we had a displacement, and I will time that by 1.1, and we do end here. That is basically now a full command file. I can run this model. Well, let's just go up and save it, and then we will go and double check the model and then run it afterwards. This concludes our tutorial on how to build a model from scratch in the Impetus AFV Solver GUI editor mode, and we hope that you have enjoyed watching. If you have any questions, please contact us via sales@certasim.com. Have a great day.